Okay.
Okay, this is lesson 17, and it's dealing with a bipolar junction transistor. So we're starting in a few of the lessons that deal with transistors. So the basic idea for a transistor is that it has three regions. It has an N region, a P region, and then another N or P. So it has two of one and one of the other. Depends on what kind of transistor you have. There are some that have two of one and one of the other, and then there are some that are the opposite. And then there are also field effect transistors. They also have three regions, but they're named differently and they behave a little bit differently. So those will be in a different lesson. So on this one, we are looking at a bipolar junction transistor, abbreviated BJT, so it's a lot shorter to say that than the three words. Basically, it has two diodes back to back. So this is what I was just mentioning. You can have an NPN or a PNP. So with this, we have an NP and a PN junction. Here we have a PN and an NP junction. So what we're going to do is draw some of these pictures so you have a little bit better idea of what's actually going on inside. There are three regions. They're named the base, the emitter, and the collector. And we're going to look at where those are in these different combinations. So in step one, it says to draw and label the regions of an NPN transistor and a PNP. So we're going to just draw a rectangle and put a small region in the middle. So this region, although it's going to be labeled as the base, it is what is also called the depletion region. So under certain circumstances, it will be depleted of the electrons in the holes or both or whatever for that particular situation. And we're not going to talk a lot about how they actually work as far as energy levels and energy bands and transitions from one energy level to another. In order to understand that, it takes quite a bit of explanation, and it's certainly something that is interesting, and particularly the ones that have a little bit more chemistry and understand energy bands and energy levels and conduction and valence bands and that sort of thing. But for now, what I'm more interested in is you getting some experience at building these circuits. So more of the electronics, more of the application idea. So I'm going to label this as N, P in the middle, N on the other side. The middle side is the base, always labeled B, and then the other two ends are collector and emitter. And for right now, it doesn't matter which way we label them, but so that everything works out in the rest of what I'm going to show you, I'm going to have this left side as the emitter and the right side as the collector. So with a PNP, we have the same sort of thing. A middle region that is an N type, a left region that's P, and a right region that's P. And I'm still going to have the emitter on the left, the base in the middle, and the collector on the right. Now, step 2 says to draw and label an NPN transistor and a PNP transistor in terms of diodes. So I'm going to keep everything here for an NPN. Okay, so with two diodes, with the N and the P, you would need to go back and look probably, I don't remember exactly which lesson, one of the other lessons, to see where the N and the P and which direction the current actually flows. So here, this is the base, and this is a diode pointing to the left. So we have the emitter, which means that the current could come out toward the left. Here, the diode is pointing the other direction, and this is the collector. So from the P to the N, that is the direction the current would flow. Now, we're going to do the same thing over here. We have a base in the middle, but since our P's and N's are reversed, then we're going to reverse these two diodes. So this diode is pointing toward the middle, and this diode is pointing toward the middle. And let's see, this is still the collector and this is still the emitter. Now, one of the things that's kind of interesting, and we're going to look at some more diagrams in just a minute on the next page, that it doesn't matter which direction the current actually flows, but this side that we're going to call the emitter is going to be the side that we look at, and current can flow either into or out of that side. But even if the current flows into that side, it's still called the emitter. Seems to me like that's kind of confusing, but that's the way that it's done. Okay, on step 3 on the next page, we're going to have another symbol. So all of these symbols they're various representations. We've looked at what actually is happening in terms of the N and P type materials. So inside the transistor, there is a material here, a different one here, and a different one here. This one is a very thin layer compared to the other two. And then this is in terms of the diode symbols. And then we're going to look at the symbol that's used in a circuit. So in a circuit, we have a line. We have a line down from that. That's the base. We have a slanted line. I'm not sure why they're slanted, but they always are. And with this arrangement, with the NPN, this does have the current flowing out the emitter. So if you notice here, current can go out the emitter, out this diode. Okay, and then this side is going to be called the collector. So over here, we're going to have the sort of the opposite. We still have the line, horizontal line. The lead from the middle of it is the base. We have a slanted line here on the left, labeled the emitter. But notice that the current goes into the base here. So we draw the arrow. And it's generally drawn, the arrow is generally drawn at the end. So if the current's going out, it's on the out end. If the current's going in, it's on the in end. So instead of putting it up here, it's usually put down here. And then this other side is called the collector. Now, we're going to go ahead and draw a couple of circuits in step 4. And then I'm also going to show you an actual transistor and where these things are located and how you tell which of the leads is which. And it is something you have to be careful about, or it's going to be easy to get things mislabeled. The base is really easy. It's the lead that's in the middle. There's no question about that one. But the emitter and the collector, you have to keep track of, because when you're looking at it one way, they're oriented one way, and when you're looking at it a different way, it's oriented differently. So I'll explain that in a minute. So now in step number 4, and these are also in your book, but I wanted to explain just a little bit about them. We're going to draw a circuit for each type of these to show you where the current goes. So this is an NPN, so I'll label that up here. I'm going to start by drawing the transistor up here and have a slanted line, we go over and down, and there's always or should be, a resistor in each of the, well, maybe not all, but some of the leads, because that's how you're going to kind of control some of the currents, is with the resistors. So this resistor is called R sub E because this side is the emitter, and with the NPN we have an arrow there. So beside, well, I'll do that in a minute. Then this is the base, and we're not going to draw a resistor there. In some circuits there will be. Then here we have one battery, and this one is going to be forward, this is forward bias. Okay. And then over here we have another battery, and it is reverse bias. So we're going to look at that and see what and why. Okay, so we have a resistor there for the collector. This is the collector, this is the base. So what happens, the base has current going into it, and I'm going to use a different color. So in this arrangement, and this shows current going out that side, so I'm going to draw a little arrow there. The current does go out that side, and for the base it goes into the base, and then what's going to happen is the collector is going to have current going into the part there. Okay, so if we look at this with forward bias, this looks fine according to our diode picture over here. We have current coming in the base and out the emitter, and that's the normal way that current will go through a diode. Okay? Now, if we look at the other side, we have this as positive, and to get a current, when this is going here, it's going opposite of what we normally have. So the diode, under normal operation, the current would be going out, but in this case the current is coming in. So you're forcing the current to come backwards through this diode. And that can be done if you have the right, I guess, combination of things. And I had mentioned before in, I don't remember which lesson, but with this, oh, actually maybe I didn't, that in one of these, the N material is lightly doped, and in the other one it is heavily doped. And there's actually some pictures and more explanation in the book that you could read through. So anyway, you have the current coming in with the reverse bias. It's coming in a direction that it normally would not come. But then we can write a current equation for that. We have the current into a junction is equal to the current out. So we would have IB plus IC is equal to IE. And this is from Kirchhoff's junction law. Okay. Now, we want to do the same thing for the other one. And Adrian, does this show all the way over there?
Yeah.
Okay. Wanted to make sure that I wasn't drawing a picture that was off into space or something. So I'm going to draw another one very similar to this, except it's going to be the PNP. So we have PNP, And we start with a transistor in the middle. We have a line up here for the emitter. We have a resistor over here. And then our reverse and forward biases are going to be switched. It's still going to be forward and reverse, but they have to be reversed here. Okay, so then this one is the base, and then we have this one. So this comes up, over, and we have a resistor RC, and this is RE, and we have the emitter here, but for the PNP, the emitter side, the current comes in, although it's still called emitter. The middle one is the base, and the one over here on the right is the collector. This is still forward, and this one is reverse. So if we want to look though and see what and why, we have current coming into the transistor here. So if we look at our PNP, on the emitter side, the current will go into the transistor. So it does come down this direction. It does come out the base, so it's the different direction. So this one with forward bias, we have current going in a circle or in a loop in a normal sense of operation. Now, for our collector, we're going to have current leaving the collector. And if you look at our diode representation, current leaving the collector is going against what we would normally expect for the diode. So that's why we have a reverse bias there so that it will actually do that. Now, let's look at our junction equation. We have two currents going into the junction and one leaving. So we have I emitter plus I base No. Okay. We have I emitter coming into the base. I have to watch my arrows. So I emitter is coming into the transistor, the junction. We have I of the base and the collector going out. So then we have IB plus IC. So I've written it differently. I've written it as in equals out and in equals out, but you notice that those are the same equations. So you have the emitter on one side and then the base and the collector on the other side. So this is all on page 144, and then there are some definitions of voltages, and then a voltage equation. There's also another term called the gain or the beta factor, and I think I will do it, let's see, I'm going to do it over here. So beta is the ratio of the collector current to the base current. Now, the whole idea for these transistors is that if you have a small base current, you can get a large emitter current, whether it's going out or coming in. And the ratio, you will also have a large collector current. So this is really what I wanted here. So this ratio of collector to base, if you can get a large collector relative to the base currents, then you have a rather large beta. So you could think of it maybe in this one as a small current coming in the base somehow persuades the electron, or not the electrons, but the holes, but persuades a rather large current to happen over here at the collector. And then those two leave together as the emitter. And this whole operation is designed to be an amplifier, so that if you can control the base current then and provide a small base current, you can end up with a rather large collector current. And I'm going to talk about this beta some at different points along the way today, but it's called the gain. It's also called the beta factor for the transistor. And when these transistors are made, when they're manufactured, they cannot be manufactured identical to each other, even if they're trying to make it happen that way. So one transistor with a particular number may have a gain of 50 or 100 or 200, and another one that was manufactured supposedly trying to be the same, it may have a beta factor, I don't know, maybe 40 or 50 or 500 or 300. So a lot of this, it's not that this beta is going to be an exact number all the time. It's not even that you necessarily want an exact beta. But the idea is it's going to be fairly large, and the result is that if you can control the base current, you can get a lot of collector current out. And so you're amplifying what you put in, and that's excuse me. That's the whole idea. So there's one more thing that I want to talk a little bit about. Let's see. I'm going to try a different color here. And this is how you look at a transistor. I'm just going to hold one up now. Adrian he doesn't, no, don't zoom in on it. I will do that later. So it's just a little bitty black thing with 3 leads on it. Okay? So we'll look at them, look at one a lot closer in just a minute. But you need to know where to put what. Okay? So we're going to look at 2 views, a bottom view and a top view. And I don't have an exact spot for that, but you might do it kind of in the space. There should be space in step 3 here. You could actually do it there if you wanted to. So it has a flat side and it has a curved side. And then if you're looking at it, let's say from the bottom view, so if you have it turned, so it's sort of sitting in your hand and the leads are pointing up, you will see 3 leads. You come out here, and this right one is the emitter, the middle one is the base, and the left one is the collector. Okay? Now, if you're looking at it like this, then obviously that's not the way you're going to use it when you put it in the circuit, because you have to turn it over so that the leads will point down. And if you do it that way, then I'm going to do it sideways here, because this is actually the orientation that you will need in the circuit, and I will show you this again. But if you turn it over so that the wires are underneath, okay, so if you imagine turning this over like that and then rotating it, You would have, oh, you have to turn it like that. Okay. Let me get my eraser here. So if you start out with it like this, so that this bottom side is the flat side, then if you turn it over and orient it like this, then the leads will be pointing into the board, and then that's what you would do, put them into the circuit board. So if you're holding it like this, with the flat edge here, and the leads pointing away from you, and I'm not going to draw dots here for that reason, because you don't see the dots. The leads will come out from behind. So this will be the collector, this one will be the emitter, and this one I'm going to draw over here will be the base. The middle one is the base, no matter what. It's just the emitter and the collector that you have to watch. So if you've got it like this, so you turn it over and around and keep the flat side there, then see this end over here on the left was the collector, so it becomes this top side, which is the collector. So you may have to look at those a little bit and think about that. Okay, so that's really all of the information, or I'd say preliminary information. We're going to go to the circuit, and I'll show you how to connect that. And then there's more that I do want to talk about as far as an analogy. But I think we need to look at the circuit and see what's going to happen there before I talk about the analogy, because then it'll make more sense, maybe. Okay, so I have already connected all of this. And I decided, instead of drawing the circuit on the board like I've done in other lessons, this one was already drawn. This is one that my husband had used, and so I thought, well, I will just use it. The one thing that you should notice, though, that when I copied it from the other Word document and pasted it into this one, there's two lines at the bottom that look like they should be grounded, and they should be, except only one little horizontal line showed up. So anyway, as we go through, you'll be able to tell which is the ground. Okay, so the first part of this, okay, no, we need to go back to the board. So let me erase all of this, now that Adrian has it all refocused. We'll have to refocus it. So I guess I will need to draw this diagram on the board. So we have over here, we have an LED. Oh, and I need to say some more about the LEDs. And then we have a resistor. Then we have our picture of the transistor. And this is what I was telling you here. There's only one line, but there should be the other lines to make that a ground. From here, there's a resistor over here to the middle of a switch. And we've used this single pole double throw switch before. So we have for the middle of it, and then one of the connection spots is here. So we have a ground, and this also has just a single line, but you might go ahead and make a couple more lines there to be obvious that it's the ground. Okay, so then we have the other side of the switch. This goes up here, and let's see, he has this labeled IC, and IB. So this is resistor B for the base. This is, I'm going to call it RC, and then this is the plus side and the minus side of the transistor. And then this goes up here 5 volts, and I'll talk about that in a minute. Okay, now what's going to happen, what we want to happen is for our LED to turn on when we move the switch up here, and for it to turn off when we have the switch down here. So we're sort of using this transistor as a switch, although we're switching over here, but the switch part here is what's turning the LED on and off. So there's a list of steps here, and in most of these transistor circuits, the general idea is that you make a few assumptions, you do some calculations to get reasonable values for various resistors, and then you actually make the exact measurements. So that's why some of this is going to seem maybe a little bit different than you're used to doing. Okay, one of the things that I will talk about a little bit later is saturation for the transistor. Now, up at the top, it's going to tell you that the voltage across the collector emitter, if that is 0.2 volts or less, then it's in saturation. But we have to calculate a few things. So what we're going to do is calculate the voltage across this resistor. Okay? But we have to assume some things. Here's the LED. Now, for the little light, the LED that you used in a previous lesson, you found that it turned on around 2 volts. So it says we're going to assume that the voltage across that is 2 volts, and we're going to calculate the voltage across the resistor. So we're going to start from here and go to up here to our 5 volts. So if we start here and go across here, and I think I'm actually going to write it down here. Voltage across the collector emitter plus the voltage across the resistor at the collector, so we have all kinds of subscripts here, plus the voltage across the LED. So if this is ground and that's 5 volts and we went along this line, then this has to be 5 volts. Okay? So we're going to calculate the voltage across the resistor, the collector resistor. VCE we're going to assume is the 0.2 volts, which it says up a little bit at the top of the page. It also says that the voltage for the LED is 2 volts. So I'm going to actually let you do a few of these calculations. They're not very complicated. So what I'm going to do though is to make sure you know what you're supposed to be solving for, although it actually tells you. So you're going to be solving this for the voltage across the collector resistor. Then in step 2 it says to calculate IC. You know that from Ohm's law, V is equal to IR. So these are all collector things. So you're going to solve for IC. So the underline means that's what you're going to solve for. Now, it says to assume that beta is 50. That's like, well, why would you assume that? We're going to assume sort of a smaller range or a smaller value for beta, and then calculate and figure out what reasonable resistors we might use in here. So you could do it for 50, you could do it for 100, it doesn't really make a lot of difference, but I decided that I would actually tell you what to use. Okay, so there was an equation, actually it's up at the top of the page, but was what I had over there, that the base current is the collector current divided by beta. I don't remember, I had it beta is collector current over base current. So anyway, you know the collector current, you will have found it from down here, and if you assume beta is 50, then you're going to solve for the base current, okay? And then if you know the base current, you can use Ohm's law and solve for that resistance. So the base resistor is going to be the base voltage divided by the base current. And then the question is, how do we get the base voltage? Well, something else that you found for the junction diode, you found that it turned on, this was in the first lesson of this unit, it turned on at around 0.6 volts. So, what we're going to do here is if we start at ground and assume that this switch is closed up here, we go from ground across the base emitter, and that's going to be 0.6 volts plus the voltage across this resistor, and then we're back to our 5 volts. So we're going to have the base emitter, and that's about 0.6 volts, plus the voltage across the base resistor has to be 5 volts, okay? So you will end up solving for the voltage across the base resistor. That goes in here, goes there, and then you solve for the base resistor here, okay? Now, the idea is that once you solve for that, that's not exactly what you're going to use, but it gives you a range or sort of a ballpark idea for what kind of resistor to put here. The main thing is you don't really want to just randomly pick resistors. I mean, that's a possibility. You could just have a whole bunch of resistors and just kind of randomly pick one and put various ones in various places. But if you do that, you're likely to either get things that don't work the way you want, or that you burn out the resistor or the LED, or you kind of in general mess things up. So we're doing what I would call approximations in order to get a reasonable number for the resistors that we're going to put in here. Okay? Now, what I will tell you is that you're going to find, if you get all the arithmetic done right, you're going to find that this is a little bit less than 10 kiloohms. Okay? So if you get something really different than that, then you haven't done your math right. Okay. So on the next page, it says to choose a resistor that's less than or equal to this. Well, there's a reason why we want a smaller resistor, and I'll talk about that again in just a little bit. The other thing is that when you decide what kind of resistor you want, you may not be able to find that if you go to Radio Shack or to wherever you buy resistors, because companies do not manufacture every single digit of resistance. So you have to pick something that's kind of in the region, the range that you want, and that's available. Well, since I have already done these calculations, I've decided, there's probably other resistors that we have, but I decided to use a 4.7K resistor. So that's what I'm going to put up here. Resistor that's used is going to be 4.7K. Now, the ones of you that I have to send these to, I sent them already on Wednesday, so you should have them on Friday, the 5th. So I thought, well, I think this is a fairly common resistor, and I looked and we did have some. So the 4 and the 7 are yellow, violet, and then notice that, remember in the color code, there's no decimal here. So this is 4, 7, and then I needed red. So 47 times 10 to the 2 is 4.7 times 10 to the 3. So your resistor should be a yellow, violet, red resistor that you're going to use in here for the base. Okay? So now I think we are going to go to the circuit and set it up, and we'll show you what you're supposed to be seeing. The first thing is, let me hold this kind of over here in the white. So this is a resistor, a transistor. Notice, if you look at it like this, you can see a flat edge and kind of a rounded side there. On the other side, you can see the 3 leads. Okay. Now, when I bought these, there were several in a pack, and there are different numbers on these. You probably need to be in a good light, and I don't know, if you're nearsighted, if you take your glasses off or your contacts out, you probably will be able to read the letters better, or read the numbers. There is a 2222, there's a 3904, and there's another one that I don't remember what is. But the one that you want to find is the one that's 3904. I think it's 2N3904. Somewhere. Oh, I may not have it on the page. I had it at the beginning though. Okay, so now we want to build our circuit. And I need to get my page that has my circuit. Okay. So we need to locate the switch that we're going to use, because that's built in. It's what we used with the capacitor, lesson 7, I think. So it's down here, and there's the little black button there that you can move up or down. On this one, there's really no middle position. So I would say we're going to use the ground position or the other position. Okay. So what I did was, this left position goes over here to this row, and this is the one I'm going to call ground. So I've got a wire from it up to the circuit board, and also from there on up to the ground, the black terminal that you've used before, the ground terminal that you've used before. Okay. Then our transistor, that's what I put in next. So if we have it right here, if you have it with the flat side to the right, which is what I had on the board, the emitter is the bottom one, the collector is the top one, and the base, I moved it out so it's back here, back behind. So I would put it in next. Separate all the little legs there and get it into the circuit board so that the emitter is in the same row as where you have the ground. Now, I have two ground wires, one coming from here up to here, and then one from here on to here, because you need to be able to connect to ground there. Okay, so then the next thing I did was the base resistor, which is the 4.7 kilo ohms, the yellow, violet, red. So we have one end of it into here, and then the other end needs to go to the middle of the switch. So I put the other end over here in this other region, and then got another wire to go from it to the middle of the switch. Remember that there are two middle columns that are equivalent, so you can use either one of those. Okay. Then so that takes care of the base and the emitter part of the transistor. So now we need the other part. So this is going up, and we decided to use a 100 ohm resistor there. We didn't really give you a choice on that. We just said that's what you're going to use. So that is the brown, black, brown. So it goes in the same row as the collector leg of the transistor. And then you have it on up here somewhere. And then you have the LED, which I'll say more about in a minute. And then the other end of the LED goes up here. And then it needs to go to the 5 volt and the positive 5 volt fixed. So notice that this red terminal says plus 5 volts. So it is plus 5 volts, and you can't change it. Remember, when you were changing voltages, you could use the yellow or the blue terminals and the knobs over here and get various voltages. But a fixed 5 volts is commonly used in dealing with transistors, so that's why they have one there. Okay, so we went from the diode up to this fixed 5 volts. The other thing is, if you look on the left part of the circuit, the 5 volts also goes to the other part of the switch. So I had another wire to go here down to this left column here on the switch. Okay, notice I have the circuit board turned off, and I have it in the down position, so that's in where it's not connecting the transistor. The other thing is that on the LED, I figured out kind of the hard way that not all the LEDs have the long and the short leads the same. So I think that the little green LED that I sent to people is like the one I have here. I have another green one, but it's a little bit darker green, and I think that this is the one like what I sent. So on that one, the long side is the one that goes up here, pointed toward the 5 volts, and the short side is the one that is connected to the resistor. So you have the long on the top, which is labeled plus, and the short on the bottom, which is labeled minus. So I guess I normally don't like to do this, but I'm going to go ahead and show you what you should end up having. And I still think you should make sure you connect the circuit and make sure that your circuit does this. Okay, so I'm going to start with my switch in the down position, and I'm going to turn my circuit board on. And when Mark was writing this a few years ago, he must have about every other step said, if you smell smoke or see smoke, turn the circuit board off and unplug it and call the instructor. Well, I did put that in there one place, but I'm hoping that you really don't have very many things like that happening. So mostly if you get things connected like I have, like I've said on the circuit diagram, and if you followed what I've done here, then you shouldn't have any problems. Okay, so you can kind of put your hand over it, and if you feel a lot of heat, then that's not good. But I don't really feel anything, I don't see anything, and we don't smell anything. So everything should be fine. Okay, so that is step 7. Now, in step 8, it says if everything seems to be fine, then you want to move the switch. So I'm going to move the switch from the down position to the up position. And what do you notice? Well, you notice no smoke, no flames or anything like that. But you should notice, and I'm not sure how easy it is for you to see this in the video, but you should notice that the LED comes on. And that's the whole idea, is that you are using the transistor to turn the LED on and off, although you are controlling this other switch. So it came on, which is what we wanted. Everything looks fine. And then we're going to use, I'm not going to do it because I've already done it, use probably, doesn't really matter which meter you use, the orange meter or the yellow meter, set at voltage, and you're going to measure the voltage across the LED and the voltage from the collector to the emitter, so it's these two sides of the transistor, and the voltage across RB, which is the base resistor, so the voltage across there, and the voltage across the collector resistor, which is the 100 ohm here, so you just measure the voltage there, and then you're going to end up calculating currents and calculating a beta. So that's what the experiment is. Now, I want to explain a little bit more. So I think I will turn that back off. And then I'm going to go back over here. I'm probably not going to draw much on the board, but to give you an idea of what's actually happening, there's an analogy that my husband had told me about, and after thinking about it, I finally figured out some more details of it that fits what we're trying to do. And this is a water faucet. So let's say the kitchen water faucet. It could also be an outside faucet that you connect the hose to water the grass. But we're just staying in the kitchen. Okay, so the idea is that when you turn on the faucet, you turn the, I just realized some of them don't turn. You have some very funny, different kinds of faucets in the kitchen nowadays. But maybe we should go outside to the, I'll get it oil in it. All the faucets, I think, outside that you connect a hose to are the ones that you turn. Okay, so you turn it a little bit, and a little bit of water comes out. You turn it some more, and more water comes out. It's like, well, that's kind of the general idea. But if you've ever done this, what happens after you've turned the faucet quite a bit? You get close to the end of how much you can turn, and the last few turns, when you turn the faucet, the water doesn't come out any faster. So you have reached what we would consider here saturation. So to begin with, when you're turning the faucet, the water that comes out, maybe the ratio of gallons per minute to how much you turn, that if you turn more, you get more water out. But toward the end, the last few turns, the water doesn't come out any faster. So this ratio, the beta that we're talking about, and in some of the later lessons, we'll have a transistor operating differently than here. For this one, we wanted as much current as we could get so that we would be sure that it's going to turn on our LED. So what we want is, or where we are, is we've got our resistors and things calculated so that this transistor is in saturation. That's what it's called. And when it's in saturation, this voltage is about 0.2 volts. So if we think about this, from ground up to here is 5 volts. That's fixed. The voltage across the LED to make it light up is fixed. So the other two things that can vary are the current, and if you have a particular resistor here, the current through this can vary and the voltage across this can vary. So now, if you have a large current here, you're going to have a large voltage here, and that's going to mean that this is a very small voltage because this plus this is going to be around 3 volts. So if your current here is such that this is almost 3, then this is very small. And that means that this is a large current, so you have a large current, and this is in saturation. Now, if you revise these things so that this current is very small, then this voltage is going to be bigger because the combination of these two voltages has to be around 3 volts. So if you have a small current, you'll have a small voltage here, and this will be bigger. But the idea is if you have a small current here, you don't have as much as you could get. And then it's not in saturation. So saturation is when you've got about all the current you can possibly get. When it's not in saturation, then it's a lesser amount. So in this circuit, we wanted saturation because we wanted a large amount of current to make sure that we could turn on the LED. In the next lesson, we're going to have the transistor operating not in saturation because we're going to be controlling various things, and it's going to be doing something quite a bit different. Now, the beta, which is the ratio of the collector current to the base current, for various transistors, it can be several hundred, as I mentioned before. But that is based on it not being in saturation. I also noticed, or I was trying to determine or measure the beta for the transistor that I was using, and I figured out on the orange meter that where you're supposed to do it, it doesn't work very well. So I don't think there's any reason why we need to measure the beta for a transistor. So we're going to make some assumptions and some calculations. I can tell you ahead of time that this beta that you get, it's a significant beta, but it's not a really large one. But it's enough that you can tell you've got a lot of current here compared to the base current, and that's kind of what we wanted. So I think that's about all I need to tell you, probably more than you wanted to know. And then we will, in the next lesson, we'll look at some more circuits.